Right. So what that means is we always need help with the 2.5-hour Chem 106 lecture, right? We always need to ask the Lord to expand our abilities and help our focus and calm our hearts so we can put the rest of our scary life aside in order to focus on this. Having just taken an exam, that makes it one notch harder. Can I have someone pray for all of us that you will and I will together be able to achieve what we need to? You come up here, and you can speak into a microphone for the few students who have to do remote.
Our Father in heaven, we're grateful for this morning. We're grateful that we were all able to arrive here in Salt Lake safely for class. Father in heaven, we would like to ask a special blessing that this morning as we listen to Dr. Ackroyd and her lecture, that our minds will be able to be calm and we'll be able to take in the concepts that we need. Father in heaven, we ask that thou may bless us in our other classes and in our jobs and internships and outside relationships. We ask that thou will be able to help us do things that maybe with our own energy we aren't capable of doing. And we ask that thou will bless those that aren't in class, either if they're sick or whatever's going on, that they may be blessed as well. And we thank thee for Dr. Ackroyd and ask that thou will bless her as she is giving us the lecture today as well. And we say these things in Jesus Christ, amen.
Amen.
Okay. I'm actually kind of excited that we get to move into it too, because two lays the foundation for what we do mostly for the rest of the course. It fits very well with year one, but it feels more to me like we're starting to. I know that's geeky, right? So I fully admit I am 100% geeky, but concepts that were 106, kinetics and the thermodynamics actually provide the foundation for chemical reactions in general. And if you really learn the concepts, you're prepared to process organic chemistry. And instead of having a scary experience in organic chemistry, you can be like, oh yeah, that makes sense. So I'm hoping to share them with you. Okay, so year one, we asked the question, how fast a reaction will go? That's kinetics, right? When we talk about kinetics, we're talking about rates and rate laws and rate constants and energies of activation and Arrhenius equation and all the different forms of the Arrhenius equation and all the different equation forms of the rate laws, right? In unit 2, we ask what is kind of a different question. Unit 2, we don't ever ask how fast does a reaction happen. What we're really asking is how much product can we expect to get from a reaction and why? So we're really asking how much product do we get or how far a reaction will go. So what does far have to do with how much product we get? We start with starting materials. The reaction proceeds towards product. So if a reaction goes farther, what do we mean? Make more product, right? Now in Chem 105, we asked you to use stoichiometric calculations to calculate percent yield, compare it to actual yield, come up with a theoretical yield, right? Remember those calculations, or do you just remember the pain involved? Okay, theoretical yield for a stoichiometric calculation, like you did in Chem 105, assumes that all starting material does what? It's used up to make product, right? So how far would that reaction go? All the way, right? The truth is that's not the way most reactions act. So unit 2 says, for a specific reaction that we're dealing with, how far will it go? How much product will it go? And actually calculate what an actual yield should be based on thermodynamics. That's what we're going to do in unit 2. And then we'll use that in unit 3 to apply to a specific kind of reaction, which is an acid-base reaction. What do you think we're going to do in unit 4? Apply that to a specific kind of reaction called the redox reaction. And because chemists have a long history of using different languages, when we go from unit 2 to unit 3 to unit 4, there will be differences in the language that we use, but the concepts are all identical. Why is that a good thing? If you master the concepts in unit 2, what will happen to you in unit 3? As soon as you master the language, you'll be like, yeah, that's not a big deal. And then what will happen in unit 4? Then you'll be really good at applying the concepts. I've actually had students in unit 4 come to me and say, this isn't anything new, right? This is just the same thing. And I go, and I've actually had at least one student who confessed to me that in unit 4, for the first reading quiz in unit 4, they didn't have time to do any of the reading, but they looked at the equations, and based on the equations and what they knew about the principles of equilibrium, they could get 100% on the reading quiz. So what does that tell you about how easy the class gets as you progress if you're really thoroughly mastering the concepts? It gets easier. Okay, flip side of that. If in unit 2, don't master the concepts, no guilt or sin imputed to you, but whatever it takes to master the concepts, you don't do it in unit 2 for whatever reason. What happens in unit 3? It gets ugly because now it's the same concepts that you don't understand and different language. And unit 4 is 4 weeks. How many weeks is unit 3? 3. How many weeks is unit 2? 2. 2 things can happen in this class. If you thoroughly make the intellectual connections, practice the skills, build a good picture of thermodynamics and how far a reaction will go, then the rest of the class gets easier and easier. If you don't, then what happens? The rest of the class gets harder and harder because you get snowed under. So word to the wise, invest whatever it takes to master unit 2. Okay, you already know a lot of where we're starting here, right? You know from what we talked about with kinetics that a reaction, when it moves forward, produces product. And once some product is formed, what can that product do? It can react backwards, right? So in any solution in which a reaction is occurring, you're going to have a forward reaction happening and at the same time a backward reaction happening, right? Okay, you also know from kinetics that the concentration of your starting material for a reaction affects how fast the reaction goes, right? So if we start with mostly starting materials, you start with the fast rate of forward reaction as the starting materials get converted to product, right? But as the reaction proceeds over time, what happens to the rate of the forward reaction? The rate of the forward reaction decreases because you've used up your starting material. So according to your rate law, your forward rate decreases, sorry. Okay, what about the rate of the backwards reaction when the product is converted to the starting material? Initially, how fast is the rate? It's very slow because you don't have very much product, right? But over time, as you make more product, what happens to the forward rate? It increases. So you have the forward rate, the rate's going down, and you have the backwards rate, and what's the rate doing? Okay, so if one is going down and one is going up, what happens when they meet in the middle? That's equilibrium. And the reason that it matters is because once the forward rate is equal to the backwards rate, then every time a product is made, a product is used up. So what happens to your concentrations after that? Stay the same. So when we're talking about how far a reaction goes, how much product gets made, that process of making product stops when? When we get to equilibrium, when the forward rate equals the backwards rate, okay? So what we see is the forward rate and the reverse rate for a given reaction change over time until finally they're equal to each other. And when they're equal to each other, the total concentration of starting materials and products cannot change after that point. That's equilibrium. Okay. Once we get to equilibrium, what happens? Can we leave equilibrium? Unless we change something, once we get to equilibrium, don't we have to stay at equilibrium? Yeah. Okay, so there will always come a point in time when the forward rate equals the backwards rate. That's equilibrium. Okay, so when we're imagining equilibrium, there are two ways to think about it. One is to think about the fact that the forward rate equals the backwards rate, right? The other one is to track the concentration, because when the forward rate equals the backwards rate, the concentration stops. So if I showed you the same kind of plot that I showed you for kinetics, where we track the concentration over time, identify equilibrium how? Where the concentrations don't change, right? Okay, so evaluate that particular reaction and then evaluate how far the reaction goes. Do we get more product or more reactant at equilibrium? Yeah, the orange line is the product because it's increasing. So we get more nitrogen dioxide. How about that question? Ask your neighbor that question and answer it.
Yeah.
Like if it's okay. So a reaction will proceed forward until the forward rate equals the backwards rate, right? Is it possible to have some reactions that proceed just a little bit forward and then the forward rate equals the backwards rate? And when they do that, what are you going to end up with at more of at equilibrium, products or reactants? Reactants. Now, as it turns out, in unit 1, we mostly showed you concentration versus time curves that reflected near product to starting material to product. So as it turns out, we have mostly up to this point shown you reactions where you end up with more product than reacted at equilibrium, but we didn't have to. So interpret the plot on your right, tell your neighbor what it means and what that plot says about where the equilibrium would lie.
When it has more reactive than equilibrium.
Yeah.
We seem to be going on conversation too.
Then I have to go back and like redo it again.
Like what is
Yeah.
Okay, so the picture on this side on the left shows an equilibrium, you end up with more product than reactant.
This
Right?
reaction's never.
What you're used to seeing. Now we have some terminology for that. If you end up with more product than reactant, what we say is, for this one, equilibrium lies on the side of products, or it's product favored. The other thing we say is equilibrium lies to the right. Why do we say equilibrium lies to the right if you get more product than reactant? We're just looking at the reaction. What side do we write the products on? The right. So if equilibrium lies to the right, we get more products than reactants. This picture here, at equilibrium, the concentration of reactants is still dramatically higher than the concentration of products. And that is not an unusual outcome. Okay, in this case, we would say equilibrium lies to the left, or equilibrium lies on the side of reactants, or this reaction is reactant favored. Don't you love how chemists always have 4 different ways to say the same things? That's frustrating at some level. It's also helpful at another level, because if one way of wording doesn't connect the idea for you, probably another word will. And as long as you know that they all mean the same thing, you're fine. Okay, make a prediction. Here's a Gibbs free energy diagram. You had to make a prediction for each of those pictures, where will equilibrium lie? To the left or to the right? That one?
Probably we're at the.
On a multiple choice exam, if you had to guess, I'm guessing that your gut would tell you that everything would rather proceed towards a lower energy state, right? So this picture should reflect equilibrium lies on the side of products. Are you right? Absolutely. Your gut is telling you the right thing. Now, this is particularly true when we're talking gives free energy as your y-axis. Potential energy can be a little more complicated, but give yourself permission to trust your gut here. If the products are lower in energy, chances are the world is going to want to proceed towards a lower energy solution, a lower energy outcome, okay? So when the product is lower and gives free energy, you're going to get more product. So what's the sign of delta G for this picture?
Negative.
You go from high to low. The delta G is negative. So when you have a negative delta G, what do you end up with? Movement towards the right, which tends to correlate with more products. Okay. Intuitively, where will the molecules want to be? Where will those atoms want to be? Higher energy or lower energy? Lower energy. So this picture, where does equilibrium lie? To the side of the reactants. Yep. Okay. Now connect this to the principle of equilibrium and relative rates and what you know of kinetics. Okay, here we have an energy diagram that goes from higher energy to lower energy. And I've drawn it as they're shown it as a gives free energy diagram, but it could also be, in this case, a potential energy diagram. For this reaction, tell your neighbor what the relative rate constants and energies of activation are for moving forward and moving backwards.
Activation.
Okay, so for the forward reaction, the energy of activation for the forward reaction for this picture is lower than the energy of activation for the backwards reaction, right? And that has to be the case because of the relative energies of products and starting materials. Okay. That also means that for this picture, because of the relative energies of activation and forwards and backwards reaction, the rate constant forward is faster than the rate constant reverse, right? Okay. That the relative rate constants forwards and backwards are going to dictate where equilibrium happens, because what's the definition of equilibrium? The definition of equilibrium mathematically is the rate forward equals the rate reverse, right? Now go back to what you know about rate laws. How do we define the forward rate? We'll assume that this is a first order reaction for the purposes of this discussion. If it's a first order reaction, then the forward rate is the rate constant forward times the starting materials, right? Okay, when we do the backwards reaction, the rate law has to include the products because we're using the products to make starting materials. So the rate of the reverse reaction is the reverse rate constant times the concentration of product, right? So when we come to equilibrium, those two things equal each other. Think about this. Relative rate constants, therefore, end up dictating what the final concentrations have to be in equilibrium. Does that make sense? So the appearance of the energy diagram and how hard it is to go forward versus backwards and those energies of activation end up dictating where equilibrium happens because of those rate constants that come out of the energies of activation. determine what the concentrations are when you get to equilibrium. Okay. Now, you know that rate constants don't change over the course of a reaction, right? In fact, the only thing we can do to change a rate constant for a given reaction mechanism is to change the temperature. So let's assume that, is the temperature going to change as the reaction progresses? Probably. Assume that it doesn't, right? Okay. So the rate constants don't change. So the concentrations that you get at equilibrium are kind of determined by the relative kinetics of the forwards and backwards reaction, right? Okay, so let's think it through for a different reaction. So remember from Unit 1 and from Chem 105 that you can have an endothermic reaction where the products end up lower in potential, higher in potential energy, lower in stability. Can that reaction kind of reaction happen? Notice that the y-axis is potential energy. So what we're doing is what we're drawing is the stability of the actual molecules. It doesn't include the entropy. So you can have a negative Gibbs free energy value for an energy diagram that looks like this. So it can still happen. Okay. So we know that the rate constant forward and the rate constant backwards are set by the energies of activation forwards and backwards. What has a higher energy of activation? The forwards or the backwards reaction? Forwards, right? So what does that tell you about the rate constant for the forwards reaction? The forwards reaction is smaller than the rate constant for the backwards reaction. Okay. So we know that the energy of activation forward is greater than the energy of activation reverse. So the rate constant forward is less than the rate constant reverse, right? Now set up your equilibrium expression. At equilibrium, this is going to be true, right? But now we know the forward rate constant is less than the reverse rate constant, right? In order for the equal sign to be true under those conditions, what that means is when it comes to equilibrium, a smaller rate constant forward has to be compensated for it by a larger starting material concentration in equilibrium. And the larger reverse rate constant has to be compensated for by a lower concentration of products at equilibrium. So this kind of potential energy diagram tends to result in more reactants than products at equilibrium. So what I'm trying to get you to do is to explicitly in your head be able to track the appearance of the energy diagram to the energies of activations, to the rate constant, to what that means about the concentrations you have to get at equilibrium. So in this case, you end up with a reaction that is reactant favored, or the equilibrium lies on the side of products, equilibrium lies to the left. Okay. Now see if you can track that logic for an exothermic reaction. Can you explain to your neighbor what the appearance of the energy diagram has to do with the energies of activation of forwards and backwards, the rate constants of forwards and backwards, and how that dictates what you're going to get more of at equilibrium? Lots of conceptual connections to make, right?
All of that. They would more activation.
Well, so the
Favoring the product.
So the.
so
They were coming, I know, and because it's exothermic, negative higher A value.
So in this case, we can tell from the appearance of the potential energy diagram that the rate constant forward is going to be higher than the rate constant reverse. So that when you set up the rate forward equals the rate reverse, like what happens in equilibrium, the rate forward can only equal the reverse rate when the concentration of products is higher than the concentration. Intuitively, can you look at that diagram and say, molecules can go forward or they can go reverse? What's easier to do, forward or reverse? Forward. So what are they going to end up with at equilibrium? More product. Okay, so the conclusions you're supposed to take is any reaction could end up with more products or more reactants at equilibrium or any ratio thereof. So there are reactions that when they come to equilibrium, there are 1 million or 1 billion or 1 trillion times more starting material than products. And the opposite is also true. You can end up with 10 to the 24th times more product than starting material, and everywhere in between. So anything is possible. And how much we end up with depends on essentially the ratio of the forward and backward. Okay, because there is such a large range of how much product and starting material you can end up with for different reactions, we need a way to communicate that, right? So if we're comparing different reactions, we need to be able to have some idea to compare exactly how much product we get. Okay, so we have this constant called the equilibrium constant. Why do we call it K?
Because it's a constant.
Because it's a constant. Constant starts with C. But what was this? What was the language of science for this word? It's actually German. And I think if I'm getting it right, constant actually is spelled with a K in German. This is why you have rate constants with a K. You have equilibrium constants with a big K. You have Boltzmann's constant, which is a little k again. Okay. Strictly speaking, we tend to write K with the equilibrium. We have to put that EQ down there. It's helpful. We have to. No, if you see a big K expressed as a Kelvin with the temperature, it's always equilibrium constant. So any big K is a version of an equilibrium. Okay, we have some ways of defining and calculating what the equilibrium constant is. Okay, so this reaction, read the reaction notation to your neighbor in terms of what's reacting and what are stoichiometric coefficients and what that tells you.
What's your name?
So this reaction is A plus B goes to C plus D. Are there really reactions called A, B, and products C and D? No, those are just stand-ins for what the actual is. Okay. The equilibrium constant. We take molar concentrations of the products and raise them to the power of their stoichiometric coefficients. Put that in the numerator. Same thing for the concentrations of starting materials and raise them to the power of their stoichiometric coefficient. Okay. Full reveal here. This is an approximation to use the molar concentrations. If we were at a higher level class, I would introduce you to the concept of activity. This is what the equilibrium constants actually come from. But for all intents and purposes, as far as you are concerned, the molar concentration expressed in moles per liter is a stand-in for the activity. And so we can calculate an equilibrium constant based on those. So these square brackets, what do those mean? Molar concentrations. Okay, full other disclosure, there are other ways of approximating activity by using concentration. This is molar concentration. If we're talking a gas in the gas phase, we can express molar concentration for things in the gas phase. Probably have blocked it from your mind from Chem 105, but partial pressure, the individual pressure of gases in a mix of gases is called partial pressure. That's a measure of the concentration of the gas as well, right? So we can also use the partial pressure of gases. Okay, so uppercase K, equilibrium equilibrium constant. Evaluate what this means. If I have a reaction where equilibrium lies to the right, what kind of equilibrium constant am I going to get?
Greater than 1.
Greater than 1. So the bigger the equilibrium constant, the more the equilibrium lies to the right, the more product you're going to get out of that reaction. Okay. So K value really tells you where does equilibrium lie? Are you going to get more products or starting materials? It also allows us, it's a number, right? You can see some fairly ugly algebra coming where I ask you to calculate for a given set of starting material conditions, exactly what will your final concentrations be? It will be a fulfillment of prophecy. So remember when your algebra teachers in high school told you that you could not live a successful life without doing FOIL in the quadratic formula? Remember that? Have they ever been right before? Will they be right here? Yes. You have to do all those things. Okay. Define, tell your neighbor what the equilibrium constant for this reaction would be equal to. How would we express it? So tell me your answer. Right. In the numerator has to be product concentrations raised to power 2. In the denominator, reactant concentrations raised to the power of 1. Okay. How about this one? So we start with our products. Product concentration is HI raised to denominator of 2. We have 2 different starting materials. They're both included in the denominator. The answer is A. Okay, here's a question for you. This is all gas phase, right? So I could use partial pressures instead. Does anyone know what the notation for partial pressure is? So if I was using partial pressure, this is what the notation would look like. I would express partial pressure of HI squared and partial pressure divided by the partial pressure of HI. It would help if I was actually writing the right thing. Okay, here's a question for you. Will the number that I get using the partial pressure be the same as the number I get using the concentration? Think back to gas phase. If you have a number for molar concentration, there's the partial pressure equals the mole fraction times the total pressure. Remember that? Is the number for the partial pressure equal to the number for the molar concentration? So will you get the same K value? You actually get a different K value, which is fine, as long as you know whether you're expressing it in terms of pressure or. Okay. Notice this. So we've already talked about this, right? Whether you get more starting materials or product at equilibrium reflects the relative rate constant. Rearrange this. You rearrange this to come up with an expression that tells you the amount of product divided by the amount of starting material. We get this, right? You rearrange this equation to express the equilibrium constant. What is it equal to? It actually equals the ratio of the forwards to reverse rate constants. So the equilibrium constant tells us how much, what the ratio is of product to starting materials, essentially. And it happens to be equal to the forward rate constant divided by the reverse rate constant. Okay. So there's all these reactions. Remember in Chem 105 how there are tables for everything? Tables for heats of combustion, and there's tables for standard molar entropies, right? There's all these tables. Chemists love tables. Well, there are huge tables for equilibrium constants. Those tables are measured. So how do chemists measure equilibrium constants? Yeah, Josh, say it louder.
Molar concentrations of the reaction at equilibrium.
Okay, this is what they do. They run a reaction, they wait till it comes to equilibrium, they measure the molar concentrations at equilibrium, and then they use those molar concentrations, they put them into the equilibrium expression, K equals yada, 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 and get a number. And that's the number they report. So how hard is it to obtain an equilibrium expression for a reaction? Not that hard. You just run it, let it come to equilibrium, measure the concentrations. Now, there are reactions where that sometimes is a little bit harder. So what if it's going to take you 3 weeks for the reaction to come to equilibrium? You don't want to do it that way, right? So how else could you do it? If you can find a way to measure the forward and reverse rate constants, that will give you the equilibrium constant. Now, I've done it in both of these ways. So in the research that I'm involved in right now, we measure equilibrium constants by doing kinetics. We measure the forward and reverse rate constants for biochemical processes and extrapolate back to get equilibrium constant this way. My PhD dissertation involved literally thousands of equilibrium constant measurements under every set of possible conditions to try to figure out what's the entropy value, what's the change in entropy, what's the change in enthalpy, what does that mean about how the reaction is actually happening. So that was the first way. Either way works fine. Okay, so the equilibrium constant ultimately is a really good way to compare different reactions to see how much product you're going to get. If this K is much, much greater than 1, what does that mean? What does much greater than 1 mean in the context of K? 10, 100, 1,000, a million, a billion. I think the largest equilibrium constant that I've seen is like 10 to the 20. That's big, right? Yeah. So would you say under those conditions, product predominates at equilibrium, right? Okay, if K is much less than 1, what do you get? What would K much less than 1 be? That means a K value with a negative exponent, right? So I'm going to show you today K values that are 10 to the minus 5, 10 to the minus 7, 10 to the minus 33. That's equilibrium lies far to the left, and you can have everything in between. Okay, for these two pictures, tell your neighbor which one reflects a K value greater than 1. Okay, K value greater than 1, product favored. You can see that intuitively, it seems like that should happen. A K value much greater than 1 reflects a forward rate constant much greater than the backwards rate constant, which corresponds to evaluate this. I picked this because it's not exactly right. If that was yours, don't feel bad. If you expressed it that way, probably there are other people in the class who are also thinking about it this way. So you're doing people a service, and you shouldn't feel bad. I don't even remember who it was because I'm not keeping track of that sort of thing. Okay, K is directly related to little k in kinetics. Is that true? Yeah. Yes. A larger rate constant K reflects a larger equilibrium constant K because as the rate constant increases, the reaction becomes more favorable. This is yes, but no. This answer is only considering the forward rate constant, right? So you have to include the backwards rate constant as well in order for this to be true. The other way that it's possible to read this is to read it as if the student is thinking that the forward rate constant is changing over time as the reaction progresses. Is that actually true? No. So this is comparing different reactions. Okay. Tell your neighbor the answer to this question. Multiple choice.
Okay, yeah, I was like.
Like, these can't all be true.
I know.
K is less than 1. Think about the ratio. What's in the numerator of the equilibrium expression? Product is in the numerator. Reactants are in the denominator. So if you have a K value less than 1, that means that the amount of product has to be less than the amount of reactant, or you wouldn't get a number less than 1. Okay, so the answer is what? One reactant. Now, here is a classic way that students' brains try to trick them to think the wrong way. We want to think that 1 is where, if K is 1, then you have the same amounts of products and reactants, and that's balanced, right? And that's equilibrium. At equilibrium, you're not necessarily going to have the same amounts of product and starting material. What you're going to have is the same rates of forwards and backwards, which usually means different amounts of starting material. Okay, tell your neighbor what you know about this reaction. So K is 200, that's a pretty big, it's a decently big equilibrium constant. So that means you have lots more products and starting materials at equilibrium, so the answer is A. Okay, be careful with this. In case, all the stoichiometries are 1, so all the powers are 1, right? So if K is big, then you know for sure there are more products and starting materials. If you have a K that's maybe hovering around 1.75 or 1.25 or 2, that's still pretty close to 1. Then the actual stoichiometries of the reaction will affect your powers, and that could affect whether 1 means equal amounts or not. Yes?
Dr. Royd, if you were to change the temperature, something different, what about the?
Okay, hold that thought. I think we're going to do that. If you change the temperature, is your K value going to stay the same? If you change the temperature, what happens to your rate constants? They change. You have a forward and a reverse rate constant with different energies of activation. Will the effective temperature be identical for both of them? No. Effective temperature changes when the energy of activation is different. So if you have a K value that actually reflects the rate constants and you change the temperature, you're going to change not just the rate constants themselves, but the ratio of the rate constants, so you're going to get a different K value. And so what I want you to notice is that very often when anyone mentions a rate constant, they tell you the temperature. So that says if K equals 298, 298K is not required to evaluate this question, but it gets reported anyway because the K is only 200 at 298K. And if you change the temperature, what do? Change the equilibrium constant. Yeah, so that's a good question. Okay, spend 10 minutes formulating those ideas on the recitation. I have printouts here. A little more slowly. What the equilibrium constant means, how we interpret it, and how we calculate it needs to be something that you don't have to think about at all.
Just briefly.
You did.
K equals 1, what does that mean?
Constant reaction structure.
One, that means, as Jacob just said, the numerator and the denominator in an equilibrium expression has to be the same as each other. Does not mean that the concentrations of individual things are necessarily the same. Not for this particular one. So we talked about how the equilibrium expression can be expressed. I guess I can take my mask off. Like, is it speaking to you that someday my friend will come? I feel like singing, someday our masks will come off.
Yeah.
I look forward to that day. Okay. And don't get me wrong, I'm very pro-mask. I'm grateful for them. I think they can make a huge difference. I'm committed to wearing mine. I just miss seeing your faces. So I look forward to a time when either so many people are infected or died, that's not an issue, or back. Cross-examine. I'm not in favor of so many people being infected. That's not what I want. Okay. We can express equilibrium constants using molar concentrations or partial pressures. And as it turns out, we have some notation that lets someone know whether you measure it with molar concentration or partial pressure. What does the T stand for? Pressure. What does the C stand for? Molar concentration. Okay, now, for a given gas phase reaction, the number that corresponds to Kp will not be the same number as the Kc. They're both describing the same equilibrium. They both will be used to calculate the same concentrations at equilibrium. But because partial pressure is a different number than molar concentration, the constants are different numbers. Okay, smart work loves questions about converting from one to the other. Can you see that whoever decided to torture students by writing smart work questions with a certain diabolical intention? So when you need Kc, they give you Kp, and when you need Kp, they give you Kc. I try to weed those questions out because I don't think they're helpful. But you do need to know that you can convert from one to the other. It's actually pretty different. It's pretty easy. Okay. It's RT with number of moles. Does that ring any gas phase bells in your mind? What should it remind you of?
Ideal gas law.
Ideal gas law, PV equals nRT. Okay, you can use PV nRT and compare mole fraction to molar concentrations and convert mole fraction to molar concentrations. And then plug those back into the equations and rearrange. What you get eventually, after playing with the gas law and the definitions of molar concentration versus mole fraction, is you get a relationship like this, where what's R, the rate? The gas constant, right? Which R do we use? There's all those different units for R. Which R do you use?
That one only.
Well, in this one, the partial pressures would be given in atmospheres, right? If what you're given is the partial pressures of the gas in atmospheres, you use that. If the partial pressures were given to you in torr, you would use the gas constant that uses torr. Would you ever use the Joule's gas constant? No, you need it expressed in terms of pressure. Okay, so we have this formula. So let's evaluate the same reaction that I showed you over and over here. They're giving you Kp, asked to calculate Kc. Okay, we know what R is. We know what T is. What's N? So if we're comparing the products to the starting materials, we say how many moles of gas in a balanced reaction in the products, how many moles of gas in the balanced reaction for the starting materials. Take the difference. What's the difference? You start with 2, you go down to 1. What's the difference? -1. Okay, because it goes down. Okay, so we have that.
The other way.
Solving for Kc, you know how to rearrange equations. You could rearrange to solve for Kc. We know that delta N is the number of gas in the products minus the number of gas in the reactants. It's -1. Plug those values in. Spend some quality time with your calculator. And end up with that's how you calculate. I don't care what the number is at the end. You don't care what the number is, so we're not even gonna calculate. Okay, here's another question. So you said if everything is a solution, how do you express your equilibrium? In terms of concentration, right? If everything is a gas, you can express your equilibrium constant in terms of partial pressures or concentration. Some of them are solids. You get to ignore the solids. Don't you love it when there's any simplifying thing? And this is the reason why. Remember I said both partial pressure and concentrations are actually a stand-in for a more theoretically rigorous measure that we call activity, right? What's the activity of a solid? 1. So anytime there's a solid in there, it would show up in the equilibrium expression as 1. So in practical terms, what do we get to do? We get to ignore it. Okay, so choose the equilibrium, the appropriate equilibrium expression. You get to leave out the calcium carbonate starting material, you get to leave out the calcium oxide product. Only things left is the single product. The stoichiometry of blend, so K equals, that's the carbon dioxide concentration. Don't you love it when more complicated allows you to be more simple?
Yes.
It doesn't always happen, we're happy about it. Okay, how about this one? So the first thing you do is say, I know I get to ignore anything that's in the solid phase. So what happens to all of our starting materials? They're not going to show up. So is there any denominator in our expression? Calcium oxide doesn't show up. So what we're left with in the numerator is carbon dioxide concentration squared times water concentration. Or I could have expressed it as the partial pressure of carbon dioxide squared times the partial pressure of water. Break.
Yes, please.
It's filled with water.
When you come back, start working on the recitation and we'll do that about 10:20 or 10:25. So a given reaction at a given temperature has a single equilibrium constant value, right? Okay. What if I change my starting material concentration? Is it still the same reaction at the same temperature? So is it still governed by the same equilibrium concentration? It doesn't matter whether you start with a lot of starting material or a little bit of starting material, or whether you start with an equal amount of products and starting materials, or if you start with all products. When it comes to equilibrium, what will those final concentrations give you? The same number. Okay, so you could say that equilibrium constant describes an individual truth about individual reactions at a single temperature. It tells you what's going to happen. One way of saying that is it predicts the future, right? Let's do an example. So here are 4 different experiments where they take the reaction that we've been looking at all day, and they set up a flask at different concentrations. So look at number 4. Here we start with 20 millimolar concentration of our starting material. So what happens over time? Your starting material gets converted to a mix of starting material and product concentrations here. And when you plug those concentrations back into your equilibrium expression, you end up with 0.213. Okay. But if instead you only start with product, you start with all product, what's going to happen initially? Backwards reaction. When you're done, the forwards and backwards rates are going to equalize out, and you're going to end up with a mix of concentrations. Take those mix of concentrations and plug them into the equilibrium expression, and what do we get? The same value. Okay, what if 1 and 2, we start with a mix of, well, so this is all product, different concentrations of product. Let it reaction go. It produces some starting material, keep some products, take those final concentrations, plug them into the equilibrium expression. Is this within the errors, the noise in the measurement, is this the same value? Yeah, it is. So you get the same equilibrium constant for a reaction at a specific temperature, no matter what concentrations you start with. No matter what mix of starting material and product concentrations you start with. Even if you start with all product, at the end, what do you get? The same value for the equilibrium concentration. Okay. What that means is if we know the equilibrium concentration, can we predict what the concentrations are going to be from at equilibrium no matter what concentrations we start with? Yes, we can. Okay, so all reactions proceed towards equilibrium. If they're already at equilibrium, they stop. If we start with all product, 100% product, are we past equilibrium? So what happens? What does the reaction do? It proceeds backwards to reach equilibrium. If we start with all starting materials, are we at equilibrium yet? No, so the reaction will proceed forward to reach equilibrium. So wherever we start from, we end up at this equilibrium position, and the equilibrium position is different for each reaction at each temperature and is described by the equilibrium constant. Okay. Back of the book, next question. So if we start with red molecules and the product is blue molecules, they say mixture 1 is at equilibrium. Can we look at an equilibrium mixture and decide what the equilibrium constant is going to be? Okay, how would we define the equilibrium expression here? Concentration of Y divided by concentration of X, right? What's the ratio Y over X for this equilibrium picture?
3.
There's 6 of our starting materials and 2 of our products. So what is our equilibrium constant here? It's 1/3. Okay, are any of these other pictures at equilibrium? How do we know? If they have a ratio of products divided by starting materials that's the same as the equilibrium picture, then they're at equilibrium too, right? Is there any of those at equilibrium? This one is. Yeah. Only this third picture has the ratio of product to starting materials that you get at equilibrium. Now these are 2 different reactions. Obviously, this is what we get for this picture. We started with more material, right? Okay, talk to me about number 2. Are we at equilibrium yet here? Are we past equilibrium?
Yeah.
So the ratio here, we have the ratio of product to starting material is what? 3/4. If the equilibrium constant is 1/3, are we past equilibrium or not to equilibrium yet? We're past equilibrium, right? So if we started from here, which direction is the reaction going to move to reach equilibrium? Move backwards. We'll revisit those concepts. Okay, so what do we know? The equilibrium constant predicts the Same concentrations at equilibrium, no matter what mix of concentrations we start with. It describes a truth about reactions. It allows us to predict what will happen, so it predicts the future. So connect this to what you learned before. What thermodynamic parameters predict the future? What predicts whether something will happen or not? The change in Gibbs free energy, right? Okay, so if K predicts what will happen, whether a reaction is going to move forward or not, and delta G or delta G naught predicts the future, what can you expect will also be true? They have to be connected, right? So K and delta G both function kind of a similar way. They kind of mean a similar thing. And in physical chemistry, if things are connected, how does that show up?
Equation.
In an equation, right? So if K and delta G tell you some of the same things and predict some of the same things, they've got to be connected. And in fact, have a connection. So the delta G naught value that you talked about in Chem 105, we'd say, is a reaction going to move forward or not? What we were really predicting is there a push from the universe to make this reaction go towards product? And it's related to the equilibrium constant. Okay. So if K is a constant at a given temperature, what do you know about delta G naught for a reaction? Mathematically, if K is a constant at a given temperature, what's delta G? It's also a constant, right? If K can't change at a given temperature, the rest of this equation, R and temperature don't change at a given temperature. So delta G naught doesn't change at a given temperature. So just like every reaction at a given temperature has a specific value of the equilibrium constant, there is a specific value for delta G naught that accompanies that reaction. Just like K tells you at equilibrium, that's a measure of how much product you're going to get at equilibrium. Does that mean delta G naught tells you the same thing? Okay. So, both constants. Easy to predict, to interpret a K. A K greater than 1 means you get a lot of product. How does that translate to the kind of delta G naught value you would get for a reaction that produces a lot of product? It's more negative. So think that mathematically the connection's through. If you get a lot of product, you get a lot more product than starting material at equilibrium. So your K value is greater than 1. When K is greater than 1, what's the natural log of K? Remember how the sign of natural logs work? You probably don't because it hasn't come up in your life before. Okay. When you're taking natural log of a number, if the number is 1, or what's the natural log of 1? 0. What's the natural log of a number greater than 1? It's positive. What's the natural log of a number less than 1, like some fraction? It's negative. Okay, so if K is greater than 1, natural log of is positive. So what's the sign of delta G? Negative. So all the things that K tells you about whether you get more product in the starting material or not, negative delta G naught tells you the same thing. Okay, if your K value is less than 1, that means at equilibrium, you're going to have more reactant than starting material, right? Which is how you get a less than 1 value for K. When you take the natural log of that K less than 1 that corresponds to equilibrium lies on the left, what's the sign of natural log of K? Negative. So take the negative of this natural log, multiply it by the negative sign in the equation. What kind of delta G naught value do you get? Positive. So if you have a reaction that gives a lot of product, you have a K greater than 1 and a negative delta G naught. Those two are inextricably linked. I want you to explicitly make the connection. If someone says equilibrium lies to the right, what does that mean about K value? Greater than 1. What does that mean about the delta G naught value? It's negative. Okay. If you have equilibrium that lies to the left, what does that mean about your K value? less than 1, what does that mean about your delta G naught value? It's positive. So I want you to bundle those things together as one idea. They're all connected to each other. They're just different ways of talking about the same thing. You know, when you read the scriptures, sometimes it says light and sometimes it says truth. Different words, slightly different concepts, same meaning, right? K and delta G naught, we express them differently, different words, slightly different meanings, but just like light and truth in the scriptures, do they tell you the same thing? Yeah. Okay, back to the question about temperature. If K is 200 at 298 Kelvin, let me know about the temperature at 400 Kelvin. When you change the temperature, what happens to your K value? Is it going to stay the same? It can't stay the same. Because remember, the rate constant is the ratio, the equilibrium constant is the ratio of the rate constants. When you change the temperature, you change the rate constants, right? But do they change the same amount? No, they don't. And in fact, depending on whether you have an exothermic or endothermic reaction, either your K forward or your K reverse is going to change the most, which means your equilibrium constant can go up as the temperature goes up, or it can go down as the temperature goes up. So we're going to talk about that next week and the week after. There's, of course, are there equations that govern that? There are. So you will have to predict that and calculate that, but what you'll see is if you connect it to the relative energies of activation, it actually makes complete sense. But keep in mind that the K at one temperature doesn't apply to another temperature. Okay, here's a question. Sometimes you're given a K value for one reaction, and you actually need the K value for the backwards reaction. Can you calculate the backwards equilibrium constant from the forwards equilibrium constant? How?
Inverse.
Okay, so forwards versus backwards reactions. This is flipping the numerator and the denominator in your equilibrium expression, because products become reactants and reactants become products, right? Okay, so in this case, if the K is 400, if you run the reaction backwards, what's the K for the backwards reaction? 1/200th, which is this one. Okay. So if you reverse the direction of the reaction, you're reversing your numerator and denominator. So you take 1 over the. So do it for this one. Don't even choose the answer. Tell your neighbor how to calculate it. They're asking the K value for this reaction. That's actually the reverse reaction for the one given above. The K for this one is 4 times 10 to the minus 2. So for this reaction, where does equilibrium lie? This is their K value. K value is 0.04. Where does equilibrium lie? On the side of 2 and right? Okay. So even without doing calculation, if you reverse the direction, where should equilibrium lie for this reaction? Still on the side of the H2 and the Br2, but on the side of products. So what should your K value be? Less than 1 or greater than 1? Greater than 1. So that one's not it. That one's not it. What is it?
C.
25. Yeah. So give yourself permission to read it for meaning and say, what do I expect should happen? Then I do the calculation. Does my calculation give me what I should expect? If it doesn't, what's likely the problem? You just did some fiddly thing wrong with your calculation and you have a chance to fix it. Jacob in the front goes, classic. Yes, it is. Classic for me as well, which is why I'm trying to teach you to think about what the numbers mean so you can stop and say, is that a reasonable answer? Here's one. How many of you in biology-based classes have seen, for example, reactions in metabolism, where the first reaction produces something and then the second reaction uses that as a starting material for the next reaction, right? Those are called linked reactions. Almost like a mechanism, except the products of one reaction are sufficiently stable on their own that we don't consider them an interim. But same idea, we produce something in one step that gets used up in the second step. And look at a product, a series of reactions like metabolism, and say, what do I start with at the beginning and what do I end up with at the end? Treat it as if it was one reaction, because all those reactions are linked. How do you calculate K for the linked reaction? We want to make a prediction. So in this case, for our net reaction here, is defined as your D concentration divided by your A concentration and your B concentration, right? What if I multiply them? What's K1 times K2? So K1, your C concentration squared, right? Divided by concentration and B concentration. If I multiply it by K2, what's K2? I have my D concentration is my numerator. What happens? Everything that is starting material in the first reaction ends up, everything that's a product in the first reaction ends up as a starting material in a subsequent reaction, right? So they're going to be on the opposite numerator and denominator side. So what happens? We cross out. So a linked reaction, you can get the equilibrium constant for the net reaction by multiplying the constants. Because then everything that shows up on both sides of the reaction in that linked reaction, what does it do when you multiply them? It cancels out. So linked reactions, you multiply the K values. Okay, so there are some K rules that you need to know without thinking about it. We've done a lot of tell your neighbor, express this, let's talk about it again, let's say it over and over today, right? Why are we doing this? It needs to be so firmly embedded in your intuition and your language that you don't have to think about it. This becomes something that you have to do without thinking about for everything that happens next. Okay, so these are all the things that need to feel pretty intuitive for you. Where are you on recitation? Let's stop and spend 10 or 15 minutes getting farther along in the recitation. Practice it for a minute. And then we will apply this to two different systems. 15 minutes of recitation. The constants have to be equal to each other, which simplest way of thinking of that is to say the energies are activated. Well, it's not as simple as that, right? Because there's like A and there's shows up in that, but simplest possible case.
Oh, okay.
That would imply actual freely molecules are identical. Since the molecules have different structures and the stability comes from different structures. Good, right?
Yeah, sure.
K equals 1. What does that tell you about the root constants in the formula? Diagram.
Do you feel like you have a good understanding of like the relationship between
little more complicated because the rate constants don't just come from it. They also come from the A values. They're much different things. The simplest way of thinking are equal to each other. That shows the rate.
Fully understand.
That would be.
Yeah.
Kind of like. plumbing.
So this one.
So for number 4, we know that.
Oh, wait. Oh, why is it? Oh, I think it's just errors.
Yeah.
It's just different one. Brilliant. That's just like one half.
K4. Oh, that's cool. Okay.
Oh, so we don't have
Yeah.
to worry about it.
That's good.
Okay, it's just one half.
I don't remember.
Oh, one half. Oh,
Right.
The month of August.
oh, it's worse.
I was just thinking.
I mean, I like sort of keep forward and look at that, but like. Oh, yeah, that's but the products, the reactants back forward. Yeah, that's really good. It's so confusing.
K4 time concentration of this K reverse one's possible. See.
Okay, I'm going to give you 2 examples of how we're going to go on to apply the constant. First one has the basis of all units. So if you had Chem 105 more than 2 years ago, at the very end of Chem 105, just before the final, it threw acid base and reduction oxidation reactions at you. Guaranteed at that stage in the semester, very few students learn, process, and retain anything. Probably don't remember. The chemistry professors finally came a little bit more to their senses and realized that was useless anyway. Took it out so that there's slightly more time to process Chem 105 material, still not close to enough time to process it, okay? So you may or may not have learned about acid-base reactions. So in an acid-base reaction, the acid actually gives off a hydrogen without its electron and transfers it to something else. If there's a reaction where an H plus becomes part of the water molecule, which makes it positively charged, leaves behind a base that doesn't have a proton. Let me draw that out in terms of what's actually happening with the Lewis diagrams. Now at this point, you're not going to be tested on whether you know what an acid is and how it works in Unit 2, but you will in Unit 3. Suppose I take a common acid, hydrochloric acid, that's what the Lewis diagram looks like. And I react it with water, for example. What actually happens? What does this bond represent? Bond. 2 electrons, right? Which means that this H can be thought of as a hydrogen nucleus with no electrons, right? And then you just have electrons in the bond. In an acid-base reaction, what happens? The proton comes off the acid, and the electrons in the bond to the hydrogen are left behind. So you end up with a negative charge on the chlorine. Was neutral, it gave up an H plus, it became negative. Okay, what does an H plus want to connect to? It needs some more electrons, right? have any electrons on the water that could interact with that H+. One of the lone pairs could be used to make a new bond to the H+, right? So we take one of the lone pairs on the water, in this case. We use that lone pair to make a new bond to the hydrogen. What actually happened is the lone pair reached out, grabbed the H+, the electrons were left behind on the chlorine, and we're left with hydronium ion. Okay, any acid characterizes as an acid because when we mix it into water, it gives its proton to water. This kind of reaction. Okay, so any acid can be depicted as H with whatever the proton is attached to. It reacts with water, it transfers the proton to water to form hydronium, and we're left behind whatever's left when the H+ comes off, right? Okay, how would you define the equilibrium constant for this reaction? Tell your neighbor.
Yeah.
So theoretically, hydronium concentration times the A- concentration divided by my HA concentration and the water. But water is the solvent, it's a liquid, right? What do we do with liquids and solids? Activity is 1, so we leave them out of the equilibrium. What we're left with is this. Now these concentrations, are they the starting concentrations or the ones we end up with at equilibrium? These are the equilibrium concentrations, right? They're not the ones we start with, they're the ones we end up at equilibrium. Okay, let me tell you that there are Ka values published for hundreds of different acids, even thousands if you characterized all the possible different acids. And those Ka values range from 10 to the minus 48 all the way to 10 to the 23rd or 24th, and everything in between. So if we look at a Ka value for a specific potential acid, what does it tell us? It tells us that when we take that acid and react it with water, are we going to get another product or not? We'll get a lot of product or not, which essentially tells us how good is the acid at giving its proton away, right? If an acid is better at giving its proton away, what happens to the Ka value? That connection? If an acid is better at transferring its proton to the water molecule, what happens to how much product you get? More product, so what happens to the Ka value? It goes up. Okay, so if you have a high Ka value, that means you get a lot of product, which tells you what about your initial acid? It was really good at giving its proton away, right? So would we consider that a strong acid or a weak acid? Strong, yes. So we use Ka values as a way of comparing the strength of different acids. There's a huge range. Everything from K is 10 to the minus 48 to K is 10 to the 23rd. And really just what that means is how reactive is that acid? Now, you regularly drink acid, right? Everyone's like, oh, I don't know about that. When you drink lemonade, it tastes tart because it's citric acid. Do you expect that is a strong acid or a weak acid? It's a weak acid, which is why you can drink it, because if it were, you were drinking strong acid, it wouldn't be good, right? Okay, so citric acid in the lemonade that you drink, what kind of Ka value is it going to have? Small, yeah. Okay, acetic acid. Anybody know what acetic acid is? It's vinegar. So usually the vinegar that you buy at the store is a 5% solution by weight of acetic acid. So not very concentrated. Ka value for acetic acid reacting with water is 1.8 times 10 to the minus fifth. Okay, how reactive is that acetic acid in water? Not very, because how much product do you get? Hardly any, right? This is why we can cook with vinegar and eat vinegar and use vinegar for cleaning, because it's actually a relatively weak acid. It's not that reactive. Okay, so is acetic acid a strong acid or a weak acid? Okay, what kind of Ka values would a strong acid have? As a minimum, greater than 1, right? The truth is, most strong acids have a Ka value of 10 or higher. How about weak acids? What kind of range do we have? There's actually not a lot of Ka values that hover around 1. So the strong acids nearly all have K values greater than 10, and the weak acids all have Ka values that are less than a tenth, and most of them are like 10 to the third, 10 to the fifth, that kind of thing. So acetic acid is a weak acid, meaning it's not very reactive because it doesn't make very much product. We can tell that from the K value. Okay, here are 4 acids. When we react each of these acids with water, we can come up with a K value. Now, sometimes there's more than one hydrogen that can be donated. So we have K value for donating the first proton and the K value for donating the second proton. That's where this covers. Evaluate those and tell me which one is the strongest acid. Yes. What is the potential pitfall here? We look for the largest number. We are tempted to compare 7.2, 1.76, 4.3, 5.6. Is that what you should be comparing? What matters the most here? Exponent. So this ammonium chloride, it actually has the smallest K value. It's the weakest acid. What's the strongest acid? HF. Okay. Hydrofluoric acid is actually what people use to etch glass. So if you see a glass that has some parts that are that are kind of cloudy and kind of pitted, they actually probably made that design by painting hydrofluoric acid onto that. Okay, so as Ka goes up, equilibrium lies more to the right side of the product, which we'll learn in unit 3. It's called on the side of the dissociated acid. Okay, here's another one that we're going to do. We are actually going to include its p values into lecture 8. So they do show up on the unit 2 exam. One reason we do this is because mathematically, these are the very best equilibrium constants to use ever. So in Chem 105, we talked about solubility a lot, right? We talked about solubility of ionic solids, and we'd say, is this going to be more soluble in water or less soluble in water? Remember those discussions? Okay, how do we measure how soluble something is in water? One way of doing that is to report what the equilibrium constant is for the solubility process for an ionic solid. Okay, so what's this formula mean? Mx equals m plus x minus. Read the code to your neighbor. What does m stand for? What does x stand for? Why is one positive and one negative? If you can remember.
These are.
So this Mx is an ionic compound, meaning that it comes from what? A positive ion and a negative ion that are held together by electrostatic interactions into a network solid. Usually, the positive ion is what? It's usually a metal. So that's why we call it M. And X is whatever non-metal, Ni. Okay. Tell your neighbor how to get, so this is a solid, right? Because we're dissolving a solid. Dissolved ions. What's your solubility constant? What's the equilibrium constant for that process? Is there anything we don't have to include?
The solid.
The solid, which means that our constant, our equilibrium constant for that process doesn't have a denominator. Okay. Why then would the chemists call that a solubility product? Because that's what they call the equilibrium constant, the solubility product. Oh, yes. What do you call something that you get from multiplying two things? A product. So is this equilibrium constant actually is a product of the two concentrations, so we call it a solubility product. Okay, so if the KSP value, the solubility product, is high, what does that tell you about how much product you're going to get? How much dissolved ions you're going to get? We'll make the connection here. For a process, if you get more product, equilibrium lies farther to the right. What does that do to your K value? It's higher. Okay, so if I have a high KSP value, is that a very soluble compound or not a very soluble compound? Very soluble. Okay, how many of you struggled to memorize the solubility rules in Chem 105?
Louise, I don't know what they are.
As with most things we memorize and don't understand where they come from, how many of you remember any of the solubility rules? Totally okay. Half the time I don't remember the solubility rules anyway. But in the solubility rules, we had three categories. We had soluble, insoluble, sometimes we have very insoluble. What that means in terms of the actual equilibrium in the process. What qualifies as soluble versus insoluble?
Positive or negative K value?
So you mean greater than 1 or less than 1, right? Okay, so if our KSP value, our equilibrium constant, is bigger, that means it's more soluble, right? If our KSP value is lower, that means we get less dissolved product, which means more of it remains as a solid, which is the same thing as saying it doesn't dissolve as well, where it's less soluble, right? But you know that there's any possible ratio of concentrations of dissolved material versus, right? So the KSP values can be any number. How do we draw the line between soluble and insoluble? Anything with a KSP greater than about 10 to the -5 is considered soluble. So I actually hate the solubility rules because there isn't any such thing as soluble or insoluble, right? There is only more soluble and less soluble. So what's the best way to think about solubility? Is it a rule? What is it? It's a constant. Okay. So here we have a table of solubility product constants. Pretty much all of those would have shown up in your list of insoluble things. Now, are they completely insoluble? If we can measure a solubility product, that must mean that enough of it dissolves that you can get enough dissolved ion that you can measure it, right? So strictly speaking, are they 100% insoluble? Okay, now look at some of the KSP values. Would you say that they are mostly insoluble? Yes. This is why in Chem 105, they would have been included in the insoluble category. But as with a lot of things in Chem 105, we simplified to the point of almost inaccuracy. Well, like think about in Chem 105, we said, what's the atomic mass unit measurement for a proton and a neutron? What did we say? Is that a lie? Well, it depends on how precise you're asked to be, right? It wasn't the whole picture. Solubility is another place where the whole picture is the equilibrium constants. It's not the rules you learn. Okay, examine the table and with your neighbor, try to identify which of the solids is the most soluble one and which one is the least soluble one. What dissolves the best? Which dissolves the least?
Yeah.
I don't know.
Right, I do. Oh, no, there's so many.
The exponent here, I what use that matters the most, right? Give the biggest sense of whether the biggest number on that table. Actually, lithium carbonate. The real value is 0.01. Okay, when you memorize the solubility rules, remember that maybe you don't remember. Groups 1 and 2 ions are generally soluble. Well, lithium is soluble. Not very, but enough to be considered soluble. Okay, what's the least soluble substance? Aluminum hydroxide is. Where is that? P-value on the range is -30. Okay, how many of you have cooked with an aluminum pot? What color is an aluminum pot? It's silver, but on the range of silver colors, what does aluminum look like in a pot? It's dull, it's not shiny, and it's more whitish. It's a lighter silver than other metals. So if you have an aluminum pot and you put it next to a stainless steel pot, the aluminum pot will look dramatically lighter in color. What you're actually seeing on the aluminum pot is aluminum hydroxide that has deposited on the outside of the pot. And it's lighter in color because you're not actually seeing metallic aluminum, you're seeing the aluminum hydroxide. Well, why can't I just wash my pot and have that layer of aluminum hydroxide fall off? Because the KSP value is 10 to the minus 33. So you can't wash it off with water. It's stuck on there. What can you wash it with? If you had a strong enough acid, you could leach off the hydroxide. I don't think vinegar has much to do with it, but you can try it. Okay. Finish the recitation. We're finishing a little bit early. I want you to be absolutely comfortable with everything we're doing. So just think about it like that. This material becomes the basis for what we do next. You're going to have to stop and think about this material at all. It's going to get harder and harder to process the next 3, 4, 6.
I didn't went over that.
This might be the only time that you have enough time to actually complete the recitation.
Well, I was trying to even just like.
Not something that I asked you to look at in the learning guide questions. But I wanted to show it to you before you encountered it in the reading, so you have one more chance to think about it. Remember we said we can use the equilibrium constant to calculate the concentrations and predict the concentrations we're going to get at equilibrium, right? How do we do that? I'm going to show you. Here's an example. Hydrogen plus iodine gas react to form hydrogen. Right? If we start with an initial concentration, this means time equals 0, an initial concentration of hydrogen equals the iodine concentration per mole. And if we're given an equilibrium constant of 64, what are our final concentrations? How are we thinking about this? So what's going to happen to our initial concentrations over time as we approach equilibrium from here? Do we have any product to start with? What direction is the reaction going to move? Forward. So what's going to happen to those concentrations? It's going to go down, right? Okay. So we can construct what we call an ice table or a rice table. You write the reaction here. Underneath it, we write our initial conditions. And then we say, okay, what's going to happen? If we start with 0.2 molar of our starting materials, the reaction is going to move forward, right? And so we're going to use up some unknown amount of our hydrogen, right? Now, I've written that I'm going to use up the same unknown amount of our iodine. How did I know that? From the stoichiometry, right? So whatever I use up at the hydrogen, I'm going to use up the same amount of the iodine because that comes from the stoichiometry of the reaction. I have written that I'm going to produce twice as much hydrogen iodide as I used up of my starting materials. How did I know? From the stoichiometry, right? For every 1 molecule of hydrogen that it used up, I'm going to produce 2 molecules of hydrogen iodide, which means however much the concentration of my starting material changes, how much it diminishes, then my concentration of product has to increase twice as much as that, right? So based on that analysis, I can say that at equilibrium, what I have is the concentration I started with minus the unknown amount that it changed for both of my initial concentrations, right? And at equilibrium, I'm going to end up with twice as much of that as my concentration. So these 0.2 minus x, 0.2 minus x, and 2x, those represent concentrations, right? Those are my equilibrium concentrations for each of my starting materials and my product. What do I know about the concentrations of starting materials and products at equilibrium for this reaction? They're going to change relative to where I started, and those final concentrations, will they give me my equilibrium constant when I plug them into the equilibrium expression? They have to, right? Okay, so this is what you do. You say, here's my equilibrium expression. And in every place, there's some brackets missing here. In every place in that equilibrium expression, I'm going to put in the unknown quantities that I know I'm going to get in equilibrium, right? So my equilibrium hydrogen iodide concentration is 2x. And my equilibrium hydrogen concentration is 0.2 minus x. And my equilibrium iodine concentration is 0.2 minus x. So I plug those in. And they have to equal 64, right? Tell your neighbor how I know that that mathematical expression can be set equal to 64.
The concentration.
Okay, so now we have a mathematical expression with a single unknown, right? Algebraically, can we solve for x? And if we solve for x, do I know how much product I'm going to make? Do I know how much starting material I have left? Yeah. How do we solve for x here? You could use the quadratic formula. There's an easier way here. If you notice, this side of the equation is a squared number. The numerator is a squared number. The denominator is a squared number. Am I allowed to just take the square root of both sides?
Yeah.
Yeah. And when you do, you get 8 equals 2x divided by 0.2 minus x. Do you have the algebraic skills to simplify and solve for x? Yes. Do you have to enjoy it? No. Totally okay to not enjoy it, but you know how to do it. You can solve for x by doing all the things that your high school algebra teacher promised you would have to know how to do. FOIL, simplifying quadratic equations, whatever. Okay, when we're done, we get a value of x equals 0.16 molar. Does this 0.16 molar answer the question?
No.
Not yet. What do we have to do? Okay, so we want to calculate all 3 equilibrium concentrations. So what is our concentration of HI at equilibrium? It's 2 times 0.160, so it's 0.32. And our hydrogen and iodine concentrations are 0.200 minus x, so we can calculate them. Okay. Could I ask you to draw me a concentration versus time curve for this reaction from certain starting material concentrations, assuming that the kinetics are first order? Yeah, I could do that. So the plot that you did in number 2 or number 3 where you had to draw, I could tell you to draw it, but not tell you the final concentration. Now you know how to calculate it. Let's do another example. Okay, this is another acid-base reaction. You don't have to know why it works. But we can say fluoride ion reacts with water, pulls a proton off of water to produce hydrogen fluoride and hydroxide ion. Okay. We know the K value is 1.5. Oh, go back to here, for example. If K is 64, should you expect more product or more starting material at equilibrium? More product. So do we get more product? Yeah. How can I, here's another thing you can do. So you can look at it and say, does this make sense? Is there a foolproof way to detect if you made a mistake? If these concentrations are correct, then when I plug them back into this equilibrium expression, what should I get? 64. Don't forget to take advantage of your foolproof check because it can catch a lot of algebra errors just by playing back. Okay, go back to our hydrogen fluoride example. So we're told K is 1.5 times 10 to the minus 11, right? If you dissolve enough sodium fluoride in water to make 150 millimolar solution, how much hydroxide are you going to get? So this dissolve in water to make 150 millimolar solution, that's our starting concentration, right? So if we do our rice table, here's our reaction. In the initial conditions, we write, this is our starting material concentration, 0.150 molar. Why am I not including what, like, there's these little funny blanks for water? How come?
Oh, it's liquid.
We're dissolving it in water, so water is a liquid. So for all intents and purposes, what do we get to do to water? All right, what's the response to that?
Yeah.
Anything we get to ignore makes life algebraically easier, so we're happy about that. Okay, so some amount of the fluoride is going to react, right? In our change, we write minus X. How do we know the reaction is going to move forward? From our initial conditions, can it move backwards? We don't have any product, can't move backwards, it can only move forwards, which means our fluoride concentration can only decrease. So the change in the concentration has to be minus X. Okay, how do we know? Tell your neighbor how we know that the product is going to be X. Temperatures are all 1. Everything that changes in the fluoride has to show up in both the hydrogen fluoride and the peroxide. So equilibrium, we get what we started with, minus the change. And we know that our equilibrium expression can be defined this way. We get to ignore the water. So it looks like this. And we know that it's set equal to 1.5 times minus 11. So we get an expression that looks like this. Carry all the x's through, so that equal to 1.5 times 10 to the minus 11. When you carry all your x's through, what kind of expression are you going to get? You're going to get a quadratic expression where you have x squared plus some constant times x plus some constant equals equilibrium constant. So what you have to do is do FOIL, then simplify. You have to solve for x. How do you solve for x if you can't take the square root of everything? Quadratic formula. We'll talk more about that next time. So solve for x. If the mention of the quadratic formula makes you begin to hyperventilate, feel free to look up how to do it. It's actually not that hard. You have to remember how. If you absolutely never want to do the quadratic formula ever in your life again, what are your options? A fancier calculator will do it for you. Okay. Solve for x. What does x tell us? In this case, tell us the hydroxide concentration. So then you're done. You can figure this one out. This is asking the question from a different direction. I've made it as mathematically simple for you as I can by setting the volume equal to 1 liter, so the number of moles equals the number of moles. Okay. What's the question asking you to solve? Asking you to solve for the equilibrium constant. To get the equilibrium constant, you have to know all the equilibrium concentrations, right? You have enough information to solve for everything in that line. They tell you that when the equilibrium is reached, 4 moles of C are produced, right? So what goes here? So what goes here? What's X? Well, 6 minus 4, 5 minus 4. So this is what we have, right? You know, we have 4 moles of C at equilibrium. So we can put 4 moles per liter in for the concentration of C. Now can we solve for the equilibrium constant? Is it even very hard? Plug it into your equilibrium expression. K value is 8. Stop at this point and say, does it make sense that my K value would be 8? If a K value is 8, what does that tell you about where the equilibrium lies? On the side of product, which means most of the starting materials get used up to make product. Is that what we see at equilibrium? We start with 6 and 5, we end up with 2 and 1. So does our answer make sense? Yeah. It does. If you want some more tutorials, I'd like this team site for kind of helping people through math. It's actually written by an AP chemistry teacher in high school, which means that he doesn't skip steps in the math. Feel free to hang around and work on recitation or to flee.
The same question. I will take the complete option.